introduce myself, since I just joined the NSSC consortium. As Professor Lucy said, I'm in the Nuclear Plasma and Radiological Engineering Department at the University of Illinois, about 140 miles south Chicago. And I work within the department in the radiological track. This is my group, so the research that you will see today is performed by the students in my group, and our general motivation is to develop radiation detection sensor and systems, as well as machine learning and statistical algorithms to really maximize the retrieved information. If you want to learn more about what we do, you can use the QR code on the bottom right to check our website. And now I'm going to go ahead and start on these applications. As we know, the nuclear energy is more and more recognized to be able to provide a sustainable source of energy for energy security and for the reduction of carbon emissions. Within this framework, I believe that advanced sensors and detection methods can support these developments in several ways by improving the fuel usage of in advanced reactors, the accountability of fuel, which is critical to make the fuel cycles proliferation resistant and safe, and to detect potential diversion of fuel promptly through, for example, the imaging of radiological sources where they should not be present through, again, imaging systems. So we have systems that can be deployed directly at the reactor site, as well as at storage sites that include dry casks and pools. And also at fabrication level to prevent any diversion, to promptly detect them and ultimately prevent diversion. And obviously at reprocessing stage, where we need to make sure that a proliferation-prone material is not used for uses, again, that are not power related, but weapons related, and by actors that are malignant. So the first application that I would like to show you is a system for the tracking and tagging of tristructural isotropic fuel in pebble bed reactors. In order to go and more in the detail of the system, I'm going to introduce their usage in PBRs. For those of you who are not familiar with it, TRISO fuel encompasses hundreds of thousands of microparticles of uranium carbide kernel, or uranium oxide kernels, within a structure that is typically made of silicon carbide. And within a single fuel pebble, which is approximately 6 centimeter diameter, you can find, again, hundreds of thousands of these kernels. This structure is extremely secure, not only because of the structural robustness of silicon carbide, but also because it keeps the fission gases within the unit. Several reactors are being designed around this fuel. And one of them is shown on the right side here. It's a pebble bed reactor where the TRISO fuel units are cycled through the core. Now, cycling these pebbles makes them usable multiple times. And in fact, among the different refueling strategies, the one where the pebbles are extracted, then measured, and then reinserted into the core is particularly useful and particularly desirable, because it allows to each single pebble to achieve the maximum burn up and therefore have high optimization of the fuel. Now, obviously, these new fuel factors present some challenges in the accountability domain, as well as in the fuel usage domain itself. So we want to detect methods that are able to tag and track these particles to make sure that none of them is diverted, although the amount of uranium is very small in each particle. And at the same time, and to support computational codes that are specifically developed to predict and for designing the reactor for the optimization of the fuel usage. So to do that, we developed a strategy that is able to accurately measure the residual amount of uranium-235 in the pebble, and also to identify a single pebble in a non-destructive way. Then we combine these two measurement techniques with a computational approach that gives us the probability of a single pebble to undergo a certain path inside the core. By combining these two, the computational and the empirical one, the experimental one, we are able with a certain accuracy to predict exactly the path that the pebble underwent inside the core. Here you can see, for example, the probable path of pebbles entering in one location here, or another location at the side, and a final location very close to the wall. These calculations were performed by our industry collaborator, Illinois Rockstar, here in Champaign, and we developed the experimental methods. And we're now in the process of combining the two. Let's now discuss the experimental methods. So you see here the pebble that I was telling you about. And our identification strategy is based on an intrinsic property of these pebbles. And the property is that the TRISO particles are randomly distributed inside it. So each distribution is a unique fingerprint that can be used to identify the pebble, as long as we can actually visualize it and detect it. To visualize it, we need to use high energy X-rays. And in particular, we used a 250 kilovolt peak X-ray scanner that is here available on our campus. And we obtained projections of some mock-up fuel pebbles that you'll see in the next slide. After we have the projections, we can reconstruct three-dimensionally the image of the pebble, and finally locate, identify the position of the particles and these unique configurations. So the relative positions are unique, and this can be used as a Pebble ID. In an application scenario, one would ID the pebble before using them, before they enter the core, and then perform this identification again as they exit the core, and be able to detect, to assign to a given pebble that initial ID. Obviously, this also requires an algorithm that is rotation invariant and can identify these configuration, these three-dimensional configurations. And we developed that too, as you'll see in a couple of slides. So the mock-up fuel pebble that we used, that was provided by BWXT, that we want to thank for that, is shown on the right top figure. And it's in fact a compact, not a pebble, but the production method is exactly the same as it would be for a pebble. So you see that it encompasses now some kernels that are tungsten-based inside the Lucite matrix. This configuration allows us to obtain a comparable attenuation coefficient to this 200 kVp X-rays that will be obtained by a typical TRISO pebble. Now, after we performed the X-ray CT, we developed our own image reconstruction, 3D reconstruction algorithms, And this allows us to clearly visualize the particle, the TRISO particle, now tungsten, but there will be TRISO particles. The next step needs to be the identification of the location of this of a single kernel, and we do that through a segmentation, so-called segmentation algorithms. Segmentation algorithms are used very often in therapeutic, radiology, and other applications. So we're familiar with those, and we apply them to this case, and we're able to exactly locate a single tungsten particle here. Afterwards, so these two algorithms were demonstrated experimentally, and then we extended our algorithms to a data set of simulated data. We don't have availability of TRISO fueled pebbles, so we simulated the 3D images that we would get from those in MCNP. And we achieved, and then we applied the 3D reconstruction, the segmentation, and ultimately the GoICP algorithm for pebble identification. And we achieved essentially a 100% successful classification ratio, even when the TRISO particles now were blurred with a noise level of 2.5 millimeter. Right, 2.5 millimeter is very large compared to the particle size itself. So this GoICP algorithm was not only successful, but also able to reconstruct the overall algorithm was able to reconstruct the pebble to 3D to generate the 3D image and locate and identify it in less than 2 minutes on a data set of 100 fuel pebbles. Obviously, many more are present in the core, so our current effort is in replacing the GoICP with more efficient machine learning algorithms that are demonstrated to have up to 500 times faster than compared to the GoICP. So we believe that even with a larger data set, we can keep the same identification time. Together with this X-ray identification algorithm, we developed a system for the assessment of the uranium-235 inside each pebble. Now, you may be familiar with the similar systems that are called multiplicity counters and are widely used in safeguards. And you can see one example on the left side. These are systems where an external neutron source is used to induce fissions on a sample, and the correlated signature is then used to assess the amount of fissile material inside the sample. And we want to do the same thing with the fresh and partially spent fuel to be able to quantify the amount of uranium-235 mass inside the TRISO particles. We then designed a new system to achieve this, which is a boron-coated straw-based multiplicity counter. The current system that we have designed and have it built by the manufacturer is based on these new types of straws, which have a corrugated surface inside. They're called the pi straws. As you can see, they have some septa inside. And these septa are important because they are coated with boron-10. And as you all know, boron-10 has a high capture cross-section for thermal neutrons. So we want to maximize the surface to have as many recoil particles that are lithium-7 and alpha particles that then we detect. And that way we detect the neutron interaction. All these straws, which are 192 in our current prototype, are embedded in a polyethylene matrix. So that is needed to slow down the the source neutrons, the neutrons from the sample, and maximize their detection probability. This system is also highly insensitive to gamma rays, which is desirable when assaying spent or partially spent fuel. This is it in the lab. As you can see, is relatively compact because the straws have a small diameter of less than a centimeter. And we detect the system, we detect the signal that is in list mode given by the array of the straw detectors. And we tested it in the lab first with a well-known californium source. So this test allowed us to validate our model, essentially the model that I showed you in the previous slide of the system. And as you can see, we have simulated and measured the Rossi alpha distribution of the neutron counts. Rossi alpha distribution shows us essentially a baseline of accidental counts due to random coincidences, and then a prompt component that you can see here due to the correlated counts. And this prompt component and its constant, its decay constant, that's called the die-away time, is a parameter of the system that in this case shows us the correlation of non-multiplying source, which is the californium one. And later on can be used for especially for multiplying assemblies to assess the multiplication. As you can see, our model resembles and models very well the measurements with a relative difference of less than 0.09% in the single count rate. So this gave us the basis to extend that model and design an even larger system that would achieve the needed efficiency for the assay of TRISO fuel pebbles. So we did that, and we also tested the system for its efficiency and its sensitivity to gamma rays. We measured at the same time that californium source that I just showed you and a cesium source. And in this plot, you can see the pulse integral response, so the spectrum that is detected by one straw with the cesium source and the californium source. As you can see, the pulses from the cesium source are much weaker compared to the neutron produced ones. So when we apply a threshold, we can easily discriminate those gamma ray pulses. This was already a relatively strong source of approximately 3 millicuries. And over 4,000 times stronger than the californium. So they gave us a good confidence that the system has that gamma insensitivity that is needed to also assess partially spent fuel that, as we know, has a very high activity due to the fission products, gamma ray emitters. So we also tested it in active mode, which is ultimately the way that it would be used using our neutron generator and using some uranium rods that have approximately 1 gram of uranium-235 each. So they have that uranium mass of the small amount that is comparable to the TRISO pebble. And as you can see here, as we increase the number of rods, we have both in the neutrons single count rates and in the correlated double count rates, a linear increase, which is highly desirable in these systems because they can be used in coincidence mode to assess the mass based on the known response of the system. As I mentioned, we scaled it up to see how many straws we would need to actually achieve the needed sensitivity and the needed response to assess the uranium-235 amount in the pebbles, the mass in the pebbles, and with an intermediate size model that we model with 396 straws, we would have already a very good singles efficiency of 13%. That would allow us to assess the uranium-235 mass in about a minute again in this active interrogation configuration. Why am I stressing here the time that these assays take? Well, because when the pebbles do recirculate within the core, we want that assessment, is the measurement, to take a very short time, less than 2 minutes, to be able to then reinsert the pebble timely if that's what's desired. So if the pebble still has a good amount of uranium that can be used, then we want to promptly reinsert it into the core. So in this project, as I had anticipated, we have developed a tracking and tagging system that encompasses a computational and an experimental part to be able to improve the fuel utilization as well as the accountability of TRISO pebbles in pebble bed reactors. Our experimentally validated model of a multiplicity counter shows the ability of assaying the uranium-235 mass in a pebble with a 0.6% uncertainty with a 100-second assay time. And the X-ray system would achieve 100% identification in less than 30 seconds for the identification and less than 2 minutes for the overall reconstruction. At the moment, we are actually expanding the multiplicity counting system to have approximately 400 straws and achieve that sensitivity that is needed in the field. So this was the first system that is meant to be used with emerging types of fuels in new reactor designs, but there are also well-established fuel cycles that we've worked on to improve the ability to track and account for fuel. And in particular, one open challenge is the assay of spent fuel in the casks, in storage casks. I'm going to go ahead and ask for questions at the end, but if you have any specific questions on this first part, I'm also happy to answer now. Okay, then see none, I'll go ahead. As I said, in established fuel cycles, the fuel form factor is very different from the TRISO one, right? And we have long rods of spent fuel, which are extremely radioactive, and that they're typically stored in dry casks at reactor pools. Given that many of these the reactors have seen extended lifetime, also the demand for casks and their transportation has increased. And there is at the moment no technique that is able to detect and visualize the cask content in a promptly way, in a short time frame, without reopening the cask. So we looked at the stages of this transportation, and what typically happens is that after the fuel is used and stays 5 to 15 years in the reactor pool, then it's loaded into a first canister that you see here on the left, and later on the canister is transported to a long-time storage location. During this transportation process, there are stages in which the fuel is enclosed in a very thick overpack that really makes non-destructive assay prohibitive and difficult, and other moments when it's only inside the canister. So we focused on these transportation stages and process where it would be possible, in fact, to use a non-destructive method to obtain a tomographic view of the inner cask without reopening, while not in the overpack, but still in the canister. So this idea here is to use a time-tagged neutron tomography. Time-tagged neutron tomography relies on so-called associated particle generators, and these associated particle generators, as they produce neutrons through the DT reaction, they're also able to detect event by event emission of the associated alpha particle. That knowledge of the angle and the direction of the alpha particle gives us also the direction of the neutron that's produced. And therefore, if we detect using an array of gamma ray detectors, the direction of the inelastic scattered gamma, we can reconstruct this triangle to find the exact location where the interaction occurred. Not only that, because if we focus on a single energy line, we can actually tag a single element where that gamma emission came from. And we tested this again in simulation and using the realistic cask model. And we were interested in seeing not only the fuel, but also potential damages to the canister. So the canister has some borated septa, which you may see here. These are borated septa, this very teeny tiny one, and then a structure, a grid of steel. So we focused on the inelastic gamma rays from iron and reconstructed the position of interaction. And as you can see here, we can identify them even if they are well inside the cask, while still being in the canister. At the moment, the canister is empty. If we then fill it up with fuel, the penetrability will be less, of course, because we have the high attenuating power of the fuel rods. But we can still reconstruct damages that are closer to the outer surface. Here you only see the canister specifically because we selected the iron line of the gamma ray inelastic scattering. But if we did not select those, then we can in fact visualize also the fuel rods that are inside the cask. This measurement would take much less than when compared to other methods such as muon tomography, although not being able in a relatively short time of a few hours, not being able to penetrate all the way inside the cask. So at the moment, we are fusing this information with neutron tomography, direct neutron tomography, and we would like to and then we would also like to incorporate further noise and non-ideality that come from, for example, from the uncertainty in the response of the detector and so on. And to be able to do that and still have an image, we're working on machine learning algorithms together with this direct reconstruction method. As I mentioned, the fuel bundles can be stored in dry casks, but they can also be stored on site and at spent fuel pools. And this is what is typically done right after the fuel is being completely used. In those cases, it's important that in those pools we maintain accountability and of the fuel of each single rod. Now, you may think that it's relatively easy to visualize a rod in a spent fuel pool. Well, it's in a general sense it is, but there are some challenges that remain even in these configurations. These challenges include the fact that, again, spent fuel is extremely active. So when we try to detect gamma rays, there's going to be a very high contribution from that bundle and surrounding bundles. And at the same time, the spent fuel is also very dense and therefore highly attenuating. One system that has been developed by the IAEA is the passive gamma ray emission tomography that is encompasses 2 detector arrays based on CCT detectors, strongly, very heavily collimated. And they rotate around the fuel bundles and reconstruct the position of the pins, the fuel rods. Now, again, this system, while being relatively sophisticated, still is affected by those problems and challenges that I mentioned before. So we worked on a simulated version of the PGT to see if we could use new algorithms to improve upon the pin localization, identification, and activity estimation. At the moment, we are collaborating with the SUC facility to analyze actually measured data. And the PGT simulation model is shown here. As you can see, the collimator is really massive compared to the detector. The detector is just the cadmium telluride, not CCT here, but the detector is a very small volume, and the collimator is this narrow green structure. These 2 modules do rotate around each single fuel bundle and allow to reconstruct and the image and visualize the integrity and the activity of the fuel. So when we solve this imaging problem with traditional algorithms, it's very difficult to correct for existing problems such as those that we mentioned, the high activity, the nuisance signal. So we developed a linear inverse approach to reconstruct this image and essentially developed a model of the system, still in Monte Carlo simulation. With the model of the system here, which is A, we aim to reconstruct the image, because in this system, if you look at it in a forward way, we would have that the fuel pins multiplied by the response matrix, by the response of the detector, would give us the detected sinogram. Plus an observation noise model using Gaussian noise. So we used a fast iterative shrinkage threshold algorithm, FISTA, to solve this inverse problem and find S given everything else, because we can measure phi and we can characterize the system response matrix. Well, characterization of the system response matrix, however, especially in simulation, in traditional Monte Carlo simulations, is extremely challenging, because we would really need to have a small source everywhere in this volume and then generate the response. So this is this would take a very long time. So we took a different approach here and developed a new Monte Carlo accelerated Monte Carlo algorithm for this application, that is the force collision. In force collision, we track both the primary gammas as well as the scattered gamma only in that field of view with the actual weights, so with the correct fractions, but only in the field of view of the detector. In this way, we can accelerate the simulation very much and obtain that response matrix that we need. As a comparison, you can see here the response to a cesium source from traditional MCNP. And this force collision detection, which takes approximately 100 times, it's approximately 100 times faster compared to the MCNP. Here we are not including the resolution of the detector. So once we do that, we have the response matrix. So we have the simulated response. And we can extract from the ground truth our image. And here you see it compared to the filter back projection. We will have some metrics to compare them, and then we can identify actually the pins. And to do that, we used a convolutional neural network that identified the pin location. And this way, an operator could compare the pin positions through different scans and multiple measurements over time, and determine whether anything was diverted. So when we identify the pins, of course, identified pins are in red circles here. We see the performance of the FBP compared to the inverse approach. These are 6 different cases of completely missing bundles, replaced fuel bundles, and 3 activities of fuel. When we compare the image quality in terms of mean square error and structural similarity, the error in the inverse approach compared to the ground truth is systematically lower compared to the FBP, and so is the similarity much higher, again, in comparison to traditional FBP. When we compare the misclassification rate as a number of misclassified pins to the total number of pins, we have, in almost all cases, a perfect classification in the case of the inverse approach. And then it doesn't perform so well in case 6, where we had different levels of the fuel rods activities. This is mainly because of the difference between the training set and the test set. The training set was, in fact, a measured data set. Without all this variability in the activities. So the system was able to, the algorithm was able to image correctly the bundle and identify the pins with high accuracy, and also to estimate the activity, because the response matrix is an absolute response. So from the number of pins, from the number of counts, we can actually extract the activity of the fuel rods. And here you see how the number of the counts in each of these 3 configurations is relatively close to the true one in the inverse approach, and generally narrower, gives us an error estimate of the actual activity compared to the FBP. This inverse approach, we're at the moment extending it to not only be able to image the single rods within a spent fuel pool, but with perhaps coarser resolution, also perform reactor monitor. And this is partially within the framework of the microreactor demonstration process, the project that is ongoing here at Illinois. And here you see a possible schematic configuration of this detection setup, which, still relying on inverse algorithms, would allow us to get a sense of the flux inside the core. And The final system that I've included in this presentation is one that we started working on right with the NSSC consortium. It is an imager. It's a highly compact imager for, at the moment, gamma rays. And I'm sure many of you are familiar with standoff imaging and Compton imaging. This is based on the same principles, where you have a sequence of detection events, and from that sequence, you can reconstruct the angle, the cone of probabilities where the source is most likely located. You see this is exemplified in this short video. Many systems do exist that exploit the same principle, but nonetheless we decided to develop our own for several reasons. Most of these systems rely on semiconductor detectors that, while being highly featuring a very high resolution, are also very expensive. So we wanted instead to work with scintillators that could give us a higher intrinsic efficiency, because they can be grown in large sizes, while keeping the whole setup really cost effective. The second innovation is using direct electronic, ASICs, existing electronic, so highly integrated without the need of digitizing and processing as each single pulse. We rely on FPGA and ASICs electronics. And finally, to be able to demonstrate on measured data the new imaging algorithms that we are working on. This system was deployed at the NCRC facility last summer, thanks to the support of the NSSC, and now the consortium fellow is working on analyzing the data. The figure on the bottom left shows you the tracking capability on a simulated data set. And the new tracking and imaging strategies that we're using are tailored to be able to not only image a source, but also track it in space. So what we aim to demonstrate is the ability of following a source, a single source, or multiple sources that move in space. And these images are, this type of reconstruction is challenging when only relying on traditional image reconstruction algorithms. And lastly, within the ASICs, we've also demonstrated that we can perform onboard the PSD without the need, again, of event-by-event digitization, as you can see in the figure on the bottom right. This means that the system can be easily upgraded to be a gamma neutron imager, again, in a very compact form factor. That's all we need. That's all you need that you see on the top right, and highly cost efficient. So being able to be deployed really everywhere with relatively low budget. So in conclusion, in our group, we detect detection systems and algorithms, and we're interested in exploiting them as much as we can with the use of advanced algorithms. So to retrieve all the signatures that the data captured. In this talk, I've showed you some applications to current, new, and well-established fuel cycles. We hope to continue working on this, and we thank the consortium of course, the National Nuclear Security Administration for the support, as well as the other sponsors that sponsor some of the work that I presented. And now I'm happy to take any questions.
Fantastic, Angela. Thank you very much for this fantastic presentation, covering actually many areas that we are interested in, particularly in the direction of advanced reactor designs. We have very different reactor designs coming out. So your methods that could actually detect what's going on inside of pebbles, inside of spent fuel assemblies, inside of cask are really fantastic, and they're helping out with non-proliferation issues. So let me see if there are questions.
Are there any curiosities or questions?
Because there are some of our students, postdocs and so on, that worked in similar areas of detection, modeling, and simulation. And you also are going into machine learning, artificial intelligence, that it might be necessary if your methodology is to be applied for thousands and thousands of pebbles that needs to be inspected and so on.
Yeah, we hope really to be able to speed up when the data set increases, because at the moment the identification scales linearly with the number of pebbles. So the larger is the data set, the more comparisons we need to make. But with the machine learning, we don't need to make that single comparison. We can focus on features. And so we hope that this will speed up the final identification, even when we have hundreds of thousands of pebbles.
There were some ideas putting specific markers on these pebbles. Would it help out in speeding up?
It would, yeah, definitely. Anything that we can, if we can add a small particle that activates, and we can tag that line, we can have additional information on burn-up, as well as location information, because we can align them better if we just have even just two would give us an axis. But in this particular effort that we had, we really wanted something that did not change the manufacturing process, and did also not affect the surface of the pebble, because anything that would be a small scratch could be a point for incipient crack or damage. So we wanted to try this completely non-destructive way, but anything else, of course, would be helpful to improve the tracking and tagging.
Excellent. You also mentioned that you could determine the amount of uranium-235. Have you considered plutonium-39?
That's a great question. So in this configuration with the active interrogation, we focused on fresh fuel and therefore induced fusion. In passive mode, however, we can correlate the multiplicities better to higher yield fissile materials such as and fissionable such as plutonium and curium.
Okay, so let's see, Tommy, do you have a question? I saw your message in the chat. So she is just thanking you, and she needs to leave. Any additional questions? One quick question for molten salt reactors. Are you considering anything related to that? Because it's very important from the point of view of accountancy of materials in this type of very interesting reactor.
Right. That's another excellent question, and I do think that at some stages of the processing, something like the multiplicity counter that we have, just because it's so insensitive to gamma rays, could be valuable. But for online molten salt, if we are dealing with very high temperatures, we do need to resort to probably different detection methods. And I'm currently investigating the use of calorimetry and this high resolution calorimetry for that.